Hello, everybody. Welcome to my astronomy seminar. Today's talk is by our PhD student Aikaterini-Niovi and it's about the formation of the Virgo Cluster.
So hello, I'm Kate, and this was the result of my internship and master thesis that I did in Aix-Marseille University. It was funded by Laboratoire d'Astrophysique de Marseille and the GECO team, which is the Galaxy Stars and Cosmology team in lab. And my master thesis was about how to search for the low surface brightness universe using bright tracers, which in my case were the planetary nebula. And with this way, we can test the hierarchical accretion in the Virgo cluster. It was supervised by Alessia Longobardi and Alessandro Buscelli, which were my supervisors during my thesis. So a galaxy in its baryonic content is composed of stars, gas, and dust. Hubble classified them based on their morphological appearance into ellipticals, lentigerous and spiral galaxies. Based on their appearance, we see simpler structures of stars on this part of his skin, going to more complicated structures of spiral arms and the bulbs as we go to the right. And irregular galaxies, we do not have any specific shape. At the time, that was interpreted as an evolutionary path that today we know it's much more complicated than what he thought. What we believe today for the evolution of galaxies is that they evolved through the hierarchical formation scenario. This means that the structures we see today formed in a bottom-up manner, from smaller structures to the bigger ones. In the universe, the smaller structures started virializing first, and with accretion and merging, they evolved into what we see today. And you probably know more about this than me. So what I am trying to trace is how these structures evolved through merging and accretion. There are different scenarios, and my research was mostly focusing on gravitational interactions, and also in the LSB features of the galaxies. There are different ways into why we are searching the low surface brightness features of the galaxies, and most importantly is because we are searching the history of how these galaxies evolve. On one manner, it's the interactions they had, and this is divided into two main parts: gravitational and hydrodynamical interactions. Gravitationally, galaxies interact with each other through merging. There are the major mergers where two galaxies of more or less the same mass collide into each other, and the momentum stops them from traveling further. Or there is minor mergers where smaller galaxies interacting with a bigger one, and this can create multiple interactions, or the bigger galaxy will target strip the smaller one, smaller satellite galaxy, and it will only leave trails of stars and dust behind. Here, you see some kind of these interactions, multiple encounters, or some that are stripped apart by galaxies. And on the other manner, hydrodynamically, galaxies, as they travel through a galactic potential, they are affected by the intercluster medium. The intercluster medium is heating up the colder gas of the galaxies, creating some trails. Creating some trails on the galaxies. And this is what is called the dynamic pressure stripping scenario. Also, in the low surface brightness features, we are searching for. We have seen traces of star formation in the diffuse gases. Here are some galaxies that, through photometry, they found out that there are star formation regions far away from the center that we used for the report. why we are investigating the low surface brightness features of the galaxies is because the focus on the outskirts of galaxies gives longer dynamical scales. What the stars of the galaxies will retain in memory is the velocity they had before the encounter. So the closer they fall to the center of the galaxy, the more prone is to lose memory of where they came from. And here are some knee-body simulations of this, simulating how far from the center of the galaxy, how fast they can be integrated in the bigger galaxy. So searching for this science in the outskirts of the galaxies, we can actually see it longer. So we see it. There are a lot of the focus on the outskirts of the galaxies because we can see it there and dynamical scales are longer, made astronomers into searching for the best quality images for this kind of researches. This means taking photometric data in the best conditions, dark sky, low zinc, low air mass, no humidity, and no moon. But this still gives a lot of limitations. First of all, in a galactic field, we cannot take all the galaxies at once with a telescope, and stacking of the images creates some bands of noise between the fields that are combined together, creating a mosaic of the whole field after. These can be easily identified as these are very vertical bands that we can deduce. But it's not only this. In the CCD camera, there can be reflections from inside the telescope that create stellar and ghost halos. Stellar are from bright stars that are in the field, or ghost halos are from the bright cores of the galaxies, and they can internally send light in the telescope and be imprinted on the CCD camera. Here are some examples of that. And as we can see, they can be easily mimic real science data and features, as the features that we're looking for are very faint. There are some researches done on that and to be reduced. Usually this kind of fake science are monochromatic and they can be reduced from the images. This is from a research done by Duke et al. That did exactly that. Also, what can mimic the LSB features is the galactic size that we simply see because we are looking from the outside from our own galaxy. And streams and features of our own galaxy can mimic science that we believe it belongs to other clusters. This is deduced by parallel researches that were done on the galactic Cyrus itself. So apart from these limitations, in order to win over the low surface brightness, there are some other ways. In my research, I focus on the bright tracers, the planetary nebula, and also there are other bright tracers such as the globular clusters. I didn't focus on them. And also there are new optics and new telescopes that are aiming for this job in order to not have the reflections inside the telescopes. And for example, there is a telescope called Castle that will start operating in Spain in spring. It's also funded by us, that's how I know. And the parallel studies that can show what is there and what is not. So in my research, as I said, I am focusing on planetary nebula. Planetary nebula are stars of mass 1-2 solar masses that have ejected their outer regions through pulsation. And as we see them from our own galaxy, they are spatially resolved sources. But when we see the planetary nebula that belong to other galaxies, they are point sources in the images. And planetary nebula are important because they have a very strong oxygen tree line that we can detect. Stars should follow the luminosities of their galaxies, and the properties of these stars should follow and the properties of the planetary nebula should reflect the physical properties of the galaxy and their environment. And this can, through this, we can see then if some interactions are the drivers of changes in the population of the galaxies. For example, if there is an isotopic galaxy that has proportionally more stars than the luminosity that we measure there, it can be a sign of interaction. Here is an example of the opposite tree line, and here is the research on the two fields of the Virgo cluster. Here is the first research that was done on MH7, and here is the research that I used for the two big fields in the Virgo cluster, and this is the Markarian chain. So, why I am focusing on the planetary nebula is because of this, what is called the alpha parameter. The alpha parameter is basically the number of planetary nebula over the luminosity of the fields of the galaxy. It correlates the integrated B minus V colors of the stellar population that's lying there, and we have seen through different researches, for example, this one of Sun in 2019, that old meteorite stellar population contain proportionally fewer planetary nebula than younger and meteor-poor galaxies. For example, here we see the values on the intercluster light of M87 and in Hall of M87. So my plan of research was, not my plan. Okay. Yeah. In my research, I focused on the local universe first because Virgo is an ideal laboratory for searching for this kind of features. It's still a dynamically young cluster that has a lot of features to see, that we can see both spatial and kinematically. We see substructures in features and plants, and we know that it's still assembling today. There are many researches dedicated on the Virgo cluster. Here is a map of all the researches that are done so far, and here is a list of different of this kind of dedicated researches. My focus was on this part of the Virgo cluster. Here is another image of it, and what I mostly used was deep broadband optical data from the research of Michos and Pirarese, and the research that was actually targeting the planetary nebula. Also, the alpha maps were used in order to deduce the galactic cirrus from the fields that I did not use, but it was used in the fields that I had. So, the VPN survey is the survey that was targeting the planetary nebula. It was 3 nights at the CFHT telescope in 2018, and it covered the 2-degree square around M87 with this resolution, and the depth for the oxygen 3-point sources was this. So 3 nights on the telescope, the orange fields are the fields that I used in my research. The rest ones are from upcoming research. And how we detect the planetary nebula is we use an on-off technique. This means we use a narrowband filter on the oxygen 3 line on the images, and we detect the planetary nebula, and then we blink the 2 images of the broadband filter and the narrowband filter to see where they are. The oxygen 3 sources can also be, because what we measure is what we detect in the photos in the narrowband filter is the redshifted oxygen 3 line, and this can be interpreted with other sources. For example, some Lyman alpha galaxies at the redshift 3 and some oxygen 2 sources, and we choose which ones are the ones that are actually planetary nebula through parallel researches in spectroscopy of the Lyman galaxies or the oxygen 2 lines that do not correspond to the same redshift that are in the Virgo cluster. So yes. So my plan for research was, in the beginning, I had the magnitude maps of the Virgo cluster and the point positions of the planetary nebula. So the first part was to create the 2D maps of the surface brightness in the Virgo cluster, and also having the positions of the planetary nebula to create maps that have the density of the planetary nebula in the regions. But this is not enough, because this accounts for all the light in the region, not the planetary nebula in the region. So I had to estimate the intracluster light contribution to the total surface brightness, and also the planetary nebula contribution that belongs to the intracluster light compared to the total planetary nebula population. Yes. And here were the first images that I had. This is the surface brightness image. We can already see some paint line and structures here. And this is the density map that I created from the positions of the planetary nebula in the region. We see that the concentrations of the planetary nebula correspond to where the galaxies are. Here is M86 and the galaxy in Markarian chain, and some concentration over here, and M87 here, of course. So first part done. The second part was to divide this the density over the region, over the surface brightness. And here we see the alpha parameter map of the whole light of the two fields. We can see already the tidal features enhanced, and actually we see them. M87 with a lot more features and plums here. The region around M86 and Markarian chain, we see a tidal feature going from M87 to the galaxies here, and a lot of more plums and structures. And we also trace values of the alpha parameter in the diffuse light. This was not enough, so we need to take into account the intracluster light component. This is the centrally concentrated component that goes as a function of the galaxies. It is a result either from galactic interactions and their stars being stripped apart, and these stars are not anymore bound to the galaxies, but they're bound to the cluster. So we measured, my supervisor had done research based on, he done research, and that the surface brightness of the intercluster light follows this law as a function of the M87, of the center of M87. So I created this map. As M87 is the biggest galaxy in the field, we took into account only M87, and we adopted the constant value for the outer regions. So we had this, and we had the intercluster light of, and we had the surface brightness of the whole region, and subtracting this from the whole from the whole surface brightness map, we only had the light that belongs to the galaxies. Also, we need to do the same thing for the alpha parameter and the proportion of the planetary nebula that only belong to the galaxies. Using this map and the alpha parameter map and the value of the alpha parameter map in a region far away from the galaxies, I estimated the number of the planetary nebula that do not belong to the galaxies. Yes, here is more comprehensive. So the total number of the planetary nebula is the ones that belong to the galaxy halos and the intercluster light. So I only had so now I had only the alpha parameter that belongs to the galaxies. What we see here, different from before, is more structures between the galaxies. We see the structure much more clearly than before. Also, these structures here, and the plants here and here. And the most important thing is this. This is a substructure that could be that we believe is an accretion event happening on M87 that was never seen before. And yeah, so we already see that with the alpha parameter we can trace what is happening in the low surface brightness with a tool that is the planetary nebula. So yes. But this was not enough, and we wanted to trace the alpha parameter in the galaxy's halos as a function of the radii of the galaxies. So I created elliptical annuli with major axes aligned to the ones of the galaxies, and I measured the alpha parameter as we go further from the center of the galaxies. In my field, I have 5 ellipticals and 1 spiral linear galaxy, and here, wait. Yeah, so this is how I measured it. And this is a random galaxy of the field. And we see that metal poor systems have higher values of alpha parameter towards the outer regions, while we see for M87 that it has several peaks that document the presence of the accreted components, such as the substructure that I showed before. Also, we see that for NTC 3443, because this one is a spiral or lenticular galaxy, we see a solar gradient, but this could be a result of an interaction because all these galaxies interact with each other, these two together and these two together. So that was the result. And yes. So with the planetary nebula and the alpha parameter from the original image, we can actually see much clearer the filaments that go from M87 to the outer regions. We can trace these plans much more clearer than in the photometric images. Here are some different values towards the core of M87 and towards the outskirts. Yes, also here some of the plans around M87, the regions around M86, and the values that are represented in my image. And seeing that the alpha parameter can be a strong tool into tracing the progenitors of these galaxies. Through this research, we also traced a new substructure in M87 that was never found before. Also, seeing as the previous plot showed, we can see that the alpha parameter can trace the metallicity and the interactions around the Markarian chain. And these results are going to be published in Astronomy and Astrophysics, but yeah, right now I haven't published because we're searching how exactly the alpha parameter is correlated with the metallicity. So we have done it for M87, but there are still some research for these galaxies because we don't have the metallicity values along their major axis. So it's going to be published soon. And yes, so to conclude. No. So yes, this research is also a continuous research. It doesn't finish to what I did. There are more things to be taken into account that are planned to be done this year and the next. Into improving the spatial coverage, the same sites, and the different types of galaxies that are a part of the research, and is aiming into tracing the planetary population into different host galaxies, for example, from giant ellipticals to very small dark galaxies, and see what is happening there. So with the further research, we aim to better constrain how the structures are formed and how they evolve. And to conclude, the planetary nebula and the bright tracers are powerful tools in order to complement studies in the low surface brightness universe, as they can trace population variations in the stellar populations and identify a variety of progenitor systems. Tracing the alpha parameter as a function of the galaxy radii, we can see that the more massive galaxies have more metal-rich underlying populations and lower values of the alpha parameter, and than less massive galaxies, but all of them grow by accretion of smaller systems. For M87, we see still that it's still growing today, even in a substantial way, and still dynamically active. And we identified a previously unknown accretion event there. So also with the alpha parameter planetary, also with the alpha parameters values, we are able to identify different progenitors that build up the halos and the intracluster-like component. And yeah, so this was the result of my research, and how it is connected to what I'm doing here is because I am interested in galaxy evolution and formation, and I want to go into more theoretical part and do computational work, so and work also with data, so that's what I'm planning to do here with Drive. The end.
Okay, thank you. Questions?
Yeah, can you go back to the results slide? Yeah. The bottom one, it shows a previously unknown accretion event.
Yes.
Can you explain how we can infer from that image that there was accretion event? What is actually, what we actually see in this image, and how do we know that it is accretion event? Just educate me. For me, if I'm looking at the image,
It's nothing. Yes.
exactly.
So in having the only photometric images we see this, where this is not, we cannot see it, it's here. This we cannot see. Having the planetary nebula, we see that there are planetary nebula that follow the light of the galaxy, but here they have stopped following it. So this shows that there is a possible interaction happening there in the past, and it has not been a part of the total of the galaxy and its luminosity.
So the blue means that there are no planetary nebulas in this region of
No, here it means that here there are more in this region than in this region in between. So something has happened here to disturb how the planetary nebula should follow if there was no accretion.
basically some of the nebulas are falling into the cluster.
Yes, it's falling into the M87, not the cluster. Yes. But it's not only the planetary nebula that are falling and they were stray. There was some galaxy before that it's having this planetary nebula and it's falling into M87.
You could take into account all the bright planetary nebula in nearby galaxies. And for faint planetary nebula, you could not take into account. How this could affect your results?
So we had two parameters. I didn't mention, but we have two parameters that estimate the loss of the planetary nebula that are not measured, and through them we estimate how many are lost, and we also take them into account in the density fields.
Sorry.
So you have a luminosity function for planetary
Yes.
nebula, but if you can apply it to locations where you see planetary nebula. If you see none, then you
You
can.
see that now. But in all of the fields, like there were planetary nebula all over most of the fields and the filaments that are traced, like where there is a galaxy stripped apart, for example, and there is a filament, the planetary nebula are following the filament, so we see it there.
Would looking into the phase space for this planetary nebula reveal any kind of information about how the substructures evolve or where they came from?
There are not on the planetary nebula, but I don't know in which stars, but in the phase of in previous researches, we see that we see this in different galaxies, but this was too far to be done for this kind of research.
They are also part of.
Yes.
You also mentioned that the M87 is connected with filaments. What do you mean by filament, because filament is.
Ah.
Directly, what do you mean? You say filament.
Okay, not the same, but this kind of structures that that is a part of light and stars that is in the intracluster light and is still falling into the galaxies or is in between the galaxies.
It's more like streams.
Streams, but we also call it filament.
Yeah. I look at it.
But those are like results of interaction between galaxies.
Yeah, it's like the debris that was left off if a smaller galaxy was falling into a bigger one. And these are parts of what the intracluster light will be composed of later when the cluster will be relaxed, more relaxed.
And they will diffuse to
Yeah.
fill the space.
Or they will go to the galaxy potential or to the cluster potential.
I understand that it's not only about other galaxies falling into M87,
Yes.
but also those coming out of it, because your first result is about streams getting out of M87. They are coming out. First result, I'm reading.
They're not really coming out of M87. This is like falling into M87.
First sentence, the first line.
No, it's yeah, okay. I mean that we see the streams coming out, but it's not the galaxies that are coming out. Yeah, I didn't notice that. But yes, it's like the streams are following this galaxy and something was happening here and it's falling to M87.
Streams are getting in, like rivers into lake.
That is what we traced. It's not the streams, it's the galaxy that might have been there before.
Is it somehow related to these so-called cold streams that there's a very well cited paper by Deckel in 2009, I think, which considers the galaxy fed by these dense cold streams that go all the way to the
But that is more or less primordial matter.
okay.
It doesn't happen in cluster centers like M87 is.
It's not cluster.
It's like earlier, in earlier epoch, were in not so dense environments.
Okay, I'm just learning about this, so I don't know.
For me, it seems that this is about the gas streams that are doing the
Yeah.
galaxy, but this is just another galaxy merging. It's
Okay.
the kind of merging that is happening, so this different type of matter, gas or stuff. At least that's my.
But where there's gas, wouldn't there also be stars?
Not definitely.
The cold stream.
There is a lot more gas.
Yeah, this is also already processed matter and planetary nebulae. I mean, the stars born, evolved, so on.
So you wouldn't see something like this in those kinds of.
Yeah, probably not. We like in this. These two galaxies here are the I galaxies, and there is some gas interaction between them that is not only through gravitational interactions, but this is not something that we are sure it is traced by the alpha parameter, so no, not for now at least.
Question? So you are primarily relying on the oxygen 8.
Oxygen
8.
3.
Oh, sorry, oxygen. 8
Explain.
yeah. 3 line to detect the planetary nebula. So what sort of observations would allow you to trace the dynamics of those streams?
Using this in spectroscopy, because now all the detections are in photometry.
Would like JPAS be enough to like say that this stream is more towards us or more receding from us?
I don't know, I didn't look, but now I'm curious. I don't know. But I think the spectroscopically maybe. Like now what we are detecting is their position because we have a narrowband filter that detects it.
What was the line? Wait,
I don't know, but it's redshifted from the oxygen tree line in the Virgo cluster, which is at 16.5 megaparsec. And the redshift is 0.004. I cannot do that.
Is it an optical line or infrared line?
Yes, yes.
Optical.
The redshift one is an optical.
I have one more question. What sort of distances will you hope to see those planetary nebula? Can you go much further than Virgo cluster?
There are researches that usually the target is the Virgo cluster or the Formax galaxy. So they're around 16, 17 megaparsecs, and like from the Earth, I'm not sure we can go for further for this kind of things.
Last ignorant question. If you want to see whether the state-of-the-art galaxy formation simulation are doing the same things, can we detect the planetary nebulas in simulation? In the galaxy formation like Eagle or Elusive, basically, simulate the galaxy.
I don't know. I do not know what is what is exactly in the simulation, so I cannot say.
I think it's not fine.
Depends on individual stellar objects in
Yes.
relation to another factor.
But if they are close,
Yeah, but this is not also individual. It's like some relate of May, but it depends how much stellar evolution they go from there. If you have like stellar evolution of nebula stars in your simulation somehow per particle, then you could see this. Yeah.
I have a question about terminology. You said something about plums. Was it?
I think it's plume.
Okay,
Yes,
because I noticed there was something called blue in one of the slides.
Yeah.
But what was it? What is? I don't know.
Plume is like a smoke or feathery smoke.
like these little things that are not galaxies, but is something that was left behind after the interaction.
Intercluster light.
Yes.
Yeah.
Not it's more concentrated than the intercluster light. Yeah, like some kind of gas and dust and stars that are not yet incorporated either in a galaxy or in the intercluster light, but there were debris from the interaction that stayed.
Like a leftover.
Yes.